Good day. Today, I will be discussing nitrogen industries. So to start, in 1774, several chemists produced oxygen but failed to realize it as a distinct element. Joseph Priestley and Carl Wilhelm Scheele discovered oxygen separately. However, for the discovery, Priestley is usually given credit. By heating mercuric oxide, Priestley and Scheele were able to produce oxygen. The gas produced from Priestley's experiments was called the phlogisticated air, and as for Scheele, it was called fire air. Antoine Lavoisier, who wrongly believed that oxygen was required to form all acids, was the one who created the name oxygen. It was first discovered and isolated by Scottish physician Daniel Rutherford in 1772. In 1790, a French chemist Jean-Antoine Claude Chaptal named nitrogen because of his experiments that showed nitrogen is a constituent of nitre, which was then called as potassium nitrate. Lord Rayleigh in 1910 discovered that an electrical discharge in nitrogen gas, active nitrogen, was produced, a monoatomic allotrope of nitrogen. Oxygen is a chemical element with the symbol O and atomic number 8. It is a highly reactive nonmetal and an oxidizing agent that readily forms oxides with the most elements as well as with the other compounds. It is colorless, odorless, tasteless gas essential to living organisms. Nitrogen is a nonmetallic chemical element that under standard conditions is a colorless, odorless, inert gas and that is used especially in the industrial synthesis of ammonia as a component of inert atmospheres and in liquid form as a refrigerant. It is also known as the fifth most abundant element in the universe. Liquid nitrogen. Liquid nitrogen is a nitrogen in a liquid state at low temperature. It is produced industrially by fractional distillation of liquid air. It is colorless, low viscosity, liquid that is widely used as a coolant. For the properties of air and constant constituents, air is a mixture of gases with 78% nitrogen and 21% oxygen with traces of water vapor, carbon dioxide, argon, and various other components. So for the uses and economy, so here are the uses and economics of oxygen. First is for the production of steel in an open hearth or basic oxygen furnaces. Next is for the removal of scale from billets by an oxyacetylene flame and in oxygen lances for cutting out imperfections. Third is for metalworking applications. Fourth is for medical purposes in hospital. Fifth is for aviators breathing oxygen. And lastly is for synthetic fuels production, specifically coal gasification and coal liquefaction. Here are the uses and economics of nitrogen. First is for the manufacture of ammonia. Next is blanketing of polymerization processes or for applications as a diluent, control of reaction rates. Third is for blanketing and bright annealing. Fourth is for food freezing, refrigerant in the processing and refrigerated transport of frozen foods. For liquid nitrogen, it includes low temperature metal treatment, shrimp fitting of parts. Third is the flashing of molded plastic and rubber parts. Fourth is cryobiology for storage of biological material such as a whole blood and ball semen. And lastly is refrigerant in cryosurgical procedures. So here are the uses and economics of nitrogen. As you can see, 40% of nitrogen is used in road transport and 0% is used in waste and solvent and product used. For manufacturing process, here is the flowchart of cryogenic process. Cryogenic process is commonly used to produce high purity products at medium to high production rates. Difference in boiling point of gases is what this technology based on. This can produce products as gases or liquids. Suction filter or filtration are provided to remove any foreign matter from the feed water which could damage either the feed pumps or the downstream plant. Next is the after cooler, that is an apparatus for cooling the discharged air from air compressors in order to remove its condensed moisture. Feed air compressor or compression. It is a device which compresses the gases to higher pressure that is used to do some mechanical work. Reversing heat exchanger. Moisture is condensed and frozen on the walls of the heat exchanger passage as the air cools. Air is cooled to near its dew point in countercurrent heat with the outgoing gaseous products. From reversing heat exchanger, air is completely dry and had over 99% carbon dioxide removed. Gel trap is used to remove remaining carbon dioxide and any hydrocarbons entering that would be hazardous. In this part, double column rectifier, cleaned air is fed to the bottom tray of the lower column. It consists of 2 tray-type distillation columns thermally connected by a heat exchanger. First is the condenser for the lower column, nearly pure nitrogen being condensed. Next is the boiler. It is placed for the upper column, full of high purity, boiling liquid oxygen. Pressure of lower column must be high enough to raise condensing temperature of nitrogen. In this part, condensed nitrogen is split from the condenser. One portion returns to the lower column as reflux, and the other is diverted to the upper column through nitrogen superheater, also used for as reflux. Oxygen-rich 35% liquid stream leaves the bottom of lower column, and after subcooled in nitrogen superheater, it serves as the main feed for the upper column. In this part, oxygen product is removed as saturated vapor from condenser. High purity nitrogen product is removed as saturated vapor from top of the upper column. In this part, nitrogen and oxygen streams are superheated approximately at 100 Kelvin. In separate non-reversing passages, high purity nitrogen and high purity oxygen are warmed. Waste nitrogen flows through passages which periodically reverse with the air passages. Thus, flows past solid carbon dioxide and frozen moisture deposited from air. It causes the deposits to sublime into the waste nitrogen and to be carried out of the heat exchanger. Expanding portion of air stream through a centrifugal expansion turbine refrigeration to overcome heat influx in the process is provided. Reheated in separate passages of the reversing heat exchanger to the proper temperature. To help maintain clean operation of the reversing heat exchanger, reheating serves to control temperature pattern. Air exhausting from the turbine is fed to the proper tray of the upper column. This is the cold box package where all low temperature equipment is assembled with piping. Some oxygen is produced by a non-cryogenic pressure swing absorption process is using a molecular sieve as the adsorbent to separate oxygen from ambient temperature compressed air. So this process produces oxygen ranging in purity from 90 to 95% and 95 to 99.9% for nitrogen. This simple process eliminates the needs for cryogenic equipment, feed dryers, regeneration heaters, and attendant utility and maintenance cost. Adsorption is the adhesion of atoms, ions, or molecules from a gas, liquid, or dissolved solid to a surface. But in this case, high-pressured air that was introduced in the first tank will pass through the sieve and nitrogen is absorbed. So when absorbing vessels achieves its capacity for impurities, the compressed air feed is automatically switched to another vessel. In operation, one vessel absorbs while the others regenerate. When the absorbing vessel achieves its capacity for impurities, the compressed air feed is automatically switched to another vessel. The first vessel then begins its regeneration cycle, which is accomplished in three successive steps: depressurizing, purging with product oxygen, and partial repressurization, after which the vessel is again ready for the absorption stage. Depressurizing allows nitrogen to dissolve or release from the sieve, while on the other hand, purging is a small amount of oxygen is used completing the regeneration of the first tank. Partial repressurization, pressure equalization with void space gas from the other beds. Impurities are rejected during the depressurization and purge steps and vented into the atmosphere. Regeneration is completed at atmospheric pressure, while adsorption and regeneration are automatic and rely only upon pressure swings for operation. So there is no need for costly heating or refrigeration. Automatic timers, pressure switches, and relays control cycling as well as product flow. Here are the hazardous effects of nitrogen. First is the inhalation of nitrogen may cause dizziness, drowsiness, nausea, vomiting, and excess salivation. It can also cause frostbite, which is the injury to body tissues caused by exposures to extreme cold, typically affecting the nose, fingers, or toes. It can also cause asphyxiation, which is the state or process of being deprived of oxygen, which can result in unconsciousness or death or even suffocation. It can There are only two companies that produces nitrogen in the Philippines. First is the Lind Philippines and the Air Liquid Philippines. Distillation of saltpeter or potassium nitrate is the usual ancient method of preparation. Nitrogen oxides are created by burning ammonia in air in the existence of a catalyst, which is the platinum, which the nitrogen oxides can be oxidized further and absorbed in water. Jabir ibn Hayyan, also known as the father of Arabic chemistry, devised and perfected sublimation, liquefaction, crystallization, distillation, purification, amalgamation, oxidation, evaporation, and filtration. He also wrote about how chemicals combined without loss of character to form a union of elements together that were too small for the naked eye to see. Johann Rudolf Glauber, born on March 10, 1604, is a German-Dutch alchemist and chemist. His discovery of sodium sulfate in 1625 led to the compound being named after him, which is the Glover salt. He also noted the formation of nitric acid from potassium nitrate and sulfuric acid. Aqua Regia, or also known as the royal water, this mixture was given its name by the alchemists because of its ability to dissolve gold and other so-called noble metals. This is primarily used to produce chloroauric acid, the electrolyte in the Wall-Hill process for refining the highest quality of 99.9% gold. Aqua regia is also used in etching and in specific analytic procedures. It is also used in some laboratories to clean glassware of organic compounds and metal particles. Nitric acid, also known as aqua fortis, Latin for strong water, and spirit of nitre, is a highly corrosive mineral acid. The pure compound is colorless, but older samples tend to acquire a yellow cast due to decomposition into oxides of nitrogen and water. Most commercially available nitric acid has a concentration of 68% in water. It is used for the manufacture of explosives, nitrocotton or gun cotton, plastics, and dyes. It is mainly used in making ammonium nitrate for fertilizers. Nitric acid is widely used as an oxidizer in liquid fuel rockets. It is used for manufacturing explosives such as TNT, gun cotton, nitroglycerin, and etc. It is also used for manufacturing fertilizers like calcium nitrate and ammonium nitrate. As you can see, 80% of uses of nitric acid is for fertilizers. Weak nitric acid production utilizes either a single or dual stage pressure system. The most common employed method is the single pressure. In a single pressure plant, air is fed into the plant, is compressed to the process pressure, and the single pressure is used in both the ammonia oxidation and nitrogen oxides absorption phases. Unlike the dual pressure process, oxidation and absorption in single pressure plants take place at the same pressure, though users can choose between high pressure and medium pressure design options. The choice will depend on your production focus. High pressure is the right choice when the focus is on producing a solution of nitric acid, while the medium pressure design option is the efficient choice for oxidation with ammonia with air to produce nitric oxide. The liquid nitrogen is first vaporized and converted into gaseous state, and then it is passed through a filter in order to remove any impurities present in the raw material. The air is compressed and passed through a heat exchanger in order to increase its temperature, and then preheated compressed air is passed through a filter to remove impurities, if any. The air and ammonia are then mixed in a mixer type equipment. Outer air is split to 85% to converter and 15% to heat exchangers and bleach column. This mixed gas is passed to the converter. The converter is the heart of the process and the first chemical reaction steps occur in this equipment. This equipment contains gases of catalysts. Platinum or platinum-rhodium catalysts are used in the process. If platinum-rhodium is used, then rhodium amount is kept at 10%. The ammonia is catalytically oxidized in presence of oxygen to primarily yield nitrogen monoxide. This is done by maintaining the reaction temperature at 920 degrees Celsius. The gases from the outlet of the converter are first cooled by passing it through the cooler, which produces 40 to 45% nitric acid as a product of 40% fixed nitrogen. And after that, the second chemical reaction step occurs, in which nitrogen monoxide gets oxidized to oxides of nitrogen, primarily nitrogen dioxide, and secondarily dinitrogen tetroxide. These are passed through a condenser in which some amount of nitric acid may be obtained. The major bulk of nitric acid is obtained in the absorption tower. The condensed nitric acid is directed into the absorption tower to get mixed with the bulk of the acid being produced. The oxides of nitrogen are passed into the absorption tower, which is continuously fed with air so as to convert more of nitrogen monoxide to oxides of nitrogen, and also continuous supply of water is maintained in such a way that the output of nitric acid from absorption tower has a concentration of 60%. The efficiency of the absorption tower increases if pressure is increased. The pressure is maintained at 10 atmosphere. Temperature of the exit gas is near 10 degrees Celsius, where two pinch points caused by kinetic problems occur within the column. Near the bottom, the rate of reoxidation of evolved nitric oxide is low. This is bleached by passing it through a column countercurrent to the 15% primary air bled off from the air compressor. So some plants include the bleach section at the bottom of the main absorber of column. The dual pressure process uses two different pressures during nitric acid production. It uses medium pressure for the compressed air used in ammonia combustion, then compresses to high pressure to optimize absorption. Through heat recovery system, heat passes and are compressed to 990 kilopascal for absorption and bleaching. The rest of the process is similar to the single pressure process. Here are the companies in the Philippines that produces nitric acid. First is the Lind Philippines, next is the MDV Airgas Trading, and Caloocan Gas Corporation. This is the end of my presentation. Thank you for listening and God bless.